So we're going to start now. So the topic in hand today is hashing. It's one of the coolest technique that you'll be encountering in data structure and algorithms. It literally solves like various problems. It makes it so easy to search, and it has various utilities. As long as you go with the progress with the goals, that you'll find that hashing comes handy every other time.
Speak up.
Yeah.
Speak up. It's hard to hear back here.
Okay, so maybe you can come away and sit over there. There's like plenty of open seats here. So if you look at the etymological meaning, it says to chop, but it has nothing to do. It's very cool, very interesting. So we'll be talking a lot about hashing techniques and the various methods that we use. But before delving into hashing, we need to understand what's the need of hashing at the first place. What's the problem in hand, and why are we even talking about hashing? So we have something called dictionaries. So like, what's the first thing that comes to your mind when we say dictionary?
Key value.
Key value. Like the basic thing that we know is like whenever we open a dictionary, we just look for a word, and for every word there is a meaning, right? So dictionary is basically an abstract data type, which is a model of database, and we store keys and values in that, and there are various operations that are supported. But before that, just let me know, like, how many of you are aware of the term abstract data type?
When you create your own attributes and operations for your data type. So like creating like classes and objects almost. So,
yeah, like it's called abstract data type because it does not have any concrete implementation. So it's just basically the idea. It is an abstraction of a data model that is represented by its behaviors. And the abstract thing is just because it is from the viewpoint of the user or the implementer. And suppose we'll be talking about various data structures like trees and so like PSTs and everything. So these are the concrete implementations of abstract data types. Like list is an abstract data type, array list is an implementation of list. So list is a data structure, and array list is a data structure, and list is the abstract data type. So yeah, so dictionary is something that stores keys and values, elements. So like, we see dictionaries everywhere, like in real world examples. So can you just name a few? Like where do you find like dictionaries? Like from, you can say from computer science domain, anywhere. Yes?
Play Store. Google Play Store. Google Search.
Google search, okay, yeah, that's true.
Student ID and student.
Yeah, network routers is also correct. Again. Yeah, somebody's mentioned that if we want to store information of a particular student, we can have his like ID as a key and all his information as a value, right? Like there are many examples, and like I've listed some of them, like telephone directory. Then we can have a particular name and a corresponding number. We can use it in library catalog, in spell checking. Like whenever we are comparing to, like spell checking is like if we usually do, right? Control F on our editor and find a certain thing, whether it's correct or not, or something like that. So we can use this dictionary thing over there. Compilers and interpreters, like probably next semester you guys will be doing that SER502, right? So it has like, you need to build a compiler and a corresponding runtime for that. So here it will have a lot of use because you need to have your own symbol table that will actually store all the identifiers and the corresponding values and everything. So it actually implements dictionary, and you'll have a lot of use there. System logging, yeah, like every time we just log into a system, we give our username and password. So back in the back end, like it stores it as a key value pair. Like for every username, there is a corresponding password. Matches it. So the various behaviors of a dictionary that we're going to call today is like size, is empty, elements. So it's basically used for searching. So we can get all the elements in a dictionary, like find elements and something like that. We can update a particular item, we can retrieve an item, and if we search for a particular key and if it's not present, it will just return like no such key is present. So we all know about the expectation from a dictionary. So can we just understand, or just can anyone tell if you a basic idea of an implementation of dictionary? How can you implement a dictionary? Like a very trivial, it would be like, I don't want a long answer or something, a simple thing. Like, what would be your approach to create a dictionary?
Simple class which are having attributes, key and value.
Okay.
Yeah, I'll have object which will have key and value. These objects.
So you can refer that object with its key and you can search it. Right? Yeah. So I'll talk about the most trivial technique that we use to implement dictionary, and that's called direct addressing, where we actually, this is actually an abstraction of an ordinary array, where we store every element if we give a particular key. So we'll be storing the information of that key in the index of the array, having that key number. So suppose is it visible to everyone?
Yes.
Suppose we have a set of keys, K1, K2, and K3. So we'll map like, since it's K0, we'll map it to 0, K1 to 1, K2 to 2. Like for every element, whatever be the key is, its corresponding index would be the same. So it's as simple as that. But there are some assumptions while doing that. The assumptions is that the key set that we are actually referring to is very slow. Like it has very limited amount of arrays, because for every key, we need to have that amount of storage in the array, right? For a particular key, we have to have that index in the array. So it's very simple. The another assumption that we have is that no two elements has the same key. So if there are two elements, it should not be having the same key. It should be different.
These keys are encrypted.
Not encrypted, that's plain and simple terms. Yeah, if you say from cryptographic domain, that would be like encrypted for encryption decryption. So as I said, the representation by direct address table or an array T. So if I refer it as T till m minus 1, so it has a size of m. So like each slot corresponding to a key in U. So this is the universe of keys, which will have many keys. So like km. So whatever be the value of the key, corresponding indices should be present in the array. If it is not present in the array and we search that, it will simply return 0. So this is basically the representation that we have a universe of keys U, and again inside this universe we have the actual set of keys that are actually going to be stored in the table, right? So as you can see, the table is from 0 to 9 index, and we are storing around 2, 3, 5, and 8. So in corresponding indices, we'll have their values. So this is very trivial, very simple. But can you just tell me, well, like, that solves the problem, right? So why are you even like bothering about hashing and other stuff? What's the problem?
Inefficient. It's like inefficient. We have to initialize 9 places even if there are 4 of them. So it's
Okay.
not the most efficient implementation.
We always need the key to delete something. We can't delete it just using the data. That needs to be deleted.
Yeah, that we need for hashing as well. Okay.
Why are you assuming keys as numbers?
So this is another thing. The keys can be non-numeric as well, right? Keys can be strings as well, but here the limitation is keys should always be numbers. Otherwise, we can't refer it. Indirect addressing. Yeah, that's another problem.
You have to use a key every time you're traversing through the data.
So, but that we need. We need to give the key to get the corresponding value. So we can't actually. So the problem is, if the universe U, like I mentioned, all possible set of keys is very large, that would be like storing that amount of keys in a table would be really problematic. Like that's not practical. Like suppose there is a problem. Like suppose a telecom provider company wants to have like caller ID facilities to all its numbers. Like it has like 8-digit numbers and it can be like millions of numbers, right? So the actual possible set of keys would be huge. So storing that amount of like having the storage for that amount of keys is quite impractical. And anyways, the company can have a very less amount of keys to be stored. The possibility is huge, but actual keys that needs to be stored may be very small. So there will be lots of wastage, as someone just mentioned.
We are storing the data as well in, like, if you have around, supposedly we have 10 keys, so we'll have 10 indexes also. So we are storing 10 indexes and we are storing 10 keys. So they are just two tables, no?
So
instead of one, we are just storing two tables, like.
So that's actually a table which will have a link and it will have containing as a key value pair, right? It will have its own key and its value. So in that particular index, I'll find that object, so which will have its key and value. But if we consider for huge amount of keys, so that's not possible and that's quite impractical. So it says the second point, the set K of keys actually stored is small compared to U, so most of the space allocated to table T will be wasted. Like we are like having so much memory for that, and we're actually storing so less, so it's completely waste. So for that problem, the requirement is we need something that will reduce that tiny universe of keys into something smaller that can be stored easily within a particular range, like from 0 to n-1, where n is the size of the table. So if we have a table with size m, then we need some function or something that will actually map all those keys into a very small range so that they can be easily inserted without any wastage or like easy retrieval. So the idea is, like, instead of you going the usual direct addressing way where we directly maps and store in the table whatever key it is, we'll use a function h and store it in the element h key. So what h is the hash function which will actually map u to a range of 0 to m-1, so that hk is actually the value that hk will be returning. It will be actually an index in the hash table. And it's represented, we say it like as like a hashes to slot hk. That's what we
As
say.
soon as we call hk, it returns a value which is already existing, or it creates a value in the hash table.
Our hash function will be implemented in such a way that will return a value which will be an index of the table. Because our hash function should map all our keys within the range 0 to m-1, and our table has the index till m-1, right? So basically, as I mentioned, like here, so it was directly mapped to here, but somewhere in between we'll have hash function for each of these keys, like h0, h1, and like h2. So all these keys will be implemented, will be put into the hash function. It will return something that will be within the range of 0 to m-1, and that way it will be stored. So that's the basic idea of hashing. And these slots will be like, it will be the value of hk2. So when we pass hk2, it's returning 2. That's why it's being stored in 2. Suppose. So if it's returning 2, then this thing will be stored in second slot.
Here, what is k in this?
In the earlier slide? So it's a general time. Like I said that if I am going to store an element of key k.
So we were using keys in this as well, no?
Yeah, that's what we're using. But the set of HK will return something that will be within the range of 0 to n minus 1. So we need not worry, right? The range has been reduced.
Using these keys only in HK. The K1.
Yeah, we'll be using the very, like suppose, like this is the actual universe of keys, and this is the actual keys that will be stored in the hash table. So it is very less. That K1, K2, something like this. But it has also keys. But we don't have to worry about all this. We'll only be referring this much, and whatever be the range, it will map it into the range 0 to n minus 1.
Just a question.
Yeah.
What if the hash function returns the same value for two different keys?
Yeah, so that's a problem we are going to discuss. So basically, in hashing, each element is stored within a location in the table, which is determined by the hashing function that we already told. So each of these location is called a bucket, and it contains both as an entry, both the key and the value. So we perform hashing on an average. It gives like a order of 1 complexity for performing insertion, deletion, and retrieval. But it's efficient for this type of operations only. But if you want to find the minimum or find the maximum or print the entire thing, so in sorted order. One more thing, we are not storing anything in a particular order. So we are just giving a key and getting it. So we are not concerned about the order. So if you need a sorted order, we might go to BST or something like that for implementing dictionary. So there was a question, there's a problem, right? So somebody said that, what if the keys are not numeric? The keys can be strings as well. The keys can be anything, any immutable thing which can't be changed. Well, mapping will have various hashing functions which actually converts into numeric things. Like if you have a string, every string can be represented as a string of bits, right? We can actually represent everything as bits, and which is actually a number. And we can actually pass that number and come up with some hash function, which will map it to the range of our hash table. And all these hashing functions, like every language, like Python or Java, has their own hash function, inbuilt hash function that we are going to use. But if we want to make our hash function more robust or more randomized, then we will probably override them. There are ways to override all those existing inbuilt hash functions. We can do that, and we can come up with our own implementation.
Can the key be a tuple? Because that's immutable as well.
Yes. I want immutable so that it can be changed.
Yes, so a tuple is immutable.
Yeah. So yeah, if you can come up with a hash function that will actually convert it into a number, so that's also possible. We talked about this. This is a basic example where you're storing a string and a corresponding number using hash function. And we are storing it in the hash table. Like for John, it has 25,000 values and is stored into 3. So we'll talk in detail how to come up with a hash function, and it's a separate thing, so we'll be covering it later. And how to write a good hash function, where there are 3 techniques. So using division, using multiplication, and using uniform hashing. So I'll be talking about that a little later. Okay, so we implemented hash table. So how is it going to help from the direct addressing? So what are the solutions that it is provided? So when k set of keys is much smaller than u, we already talked, hash table requires much less space compared to direct address table. The storage requirements can be reduced to 0 of k because k is actually the set of whatever keys will be actually stored. And the average searching for an element request is order of 1. Having some assumptions, obviously. It's not the worst case, it's only the average one. So hash function should be something, it should be very simple to compute, and it should have all the keys distributed evenly. So there is a concept called simple uniform hashing, which says that every key, the key set, must be equally likely every key should be mapped, should be equally likely mapped to any of the slots, irrespective of the earlier keys like present. So if this thing can be mapped to this slot, the probability will be similar for this one. So the probability will be, it is the size of m. So for every key, it can go to any of those slots. It would not have any impact on the earlier hashed keys. So for each one of them, it will be 1 by n. So hash function we are going to cover a little later. It has various methods. So somebody said, what if the hash key function actually maps to similar values, right? We have two hash functions which are actually pointing to the same slot. So in that scenario, we'll have a collision. A collision is something like, as you said, like when an element is inserted, it hashes to the same value as like something already have been inserted. So what to do then? So we need to resolve it. This is a serious issue with hashing, and we have practically two approaches for solving it. We can use separate chaining and we can use open addressing. So in separate chaining, we basically use a linked list to store everything that are actually mapped to the same slot. So this is, we are going to talk about it in detail. So from that set K of actual keys, so there might be some keys, like here we have K1 and K4, which are actually mapping to the same slot, right? Yeah.
How do you choose the set K from the universe of K?
We are not choosing, it's just that, like I said, like the telephone company problem, that it has 8-digit numbers, right? So what are the possibilities? So if it's a decimal 10 to the power 8 minus 1 type of possible keys that can actually exist in the universe. That's our universe of keys. But there may be very small number of people who are actually subscribed to the telecom provider. The actual keys in implementation that needs to be stored might be very less. So that's how we come with the K, the smaller set.
Isn't that the case with direct addressing also? We are only using the keys which we are mapping to the indexes.
Yeah, but in direct addressing, our whole universe is this. The scope is limited. So we are assuming that universe is not that big. That was the assumption that we take during direct addressing. And also that none of the two keys will have same value. So we are answering this like, what if they have the same value?
No, but in direct addressing and hashing, in both of them we are using only the keys which are mapping to the indexes actually. So I'm not able to figure out the difference between
But
them.
for hashing, we are actually, if it has a key K1, it will be directly stored into the 1th index. But in hashing, we are actually passing it into the hash function. The hash function will be returning something else. Like K1 can be, the hash function can return maybe 2, 3 or something else. It has no dependency on the
But the problem was the universe, no?
Yes.
We had too many keys in the universe. So how is that problem solved over here? We are using as many keys in both of them.
Yeah, but as many keys as in both of them, but the table that I'm using, the size that I'm taking, is only like to the length of the key set, like whatever key I have in K, not the universe. But in direct addressing, we are actually taking the hash table size, the whole, the entire universe. So we are assuming that our universe is very small. That's how we came to the direct addressing problem. And now if we take in the real world problem where the universe will be too big, we'll be using hashing. Okay. So this is what if K1 and K4 actually maps to the same slot. So here we are using a linked list, and every time we encounter a particular key having a similar value, or then already some key might have already the same value earlier, then we'll append to that list. We'll store that, first of all, like maybe K4 has been inserted first, So it got stored into the list, and then again K1 also mapped to the same slot. Then it will only be added to the front of the list. So it like this. So all other slots, there might be various like empty slots as well, but here K1 and K4 are actually mapping to the same slot, so they will be appended to the linked list. I think it's pretty simple and clear. The only good thing about this, only the bad thing is about this, we need to like get dependent on something extra. So our hash table will have a link to the a pointer to the linked list, head of the linked list, and it will traverse that way. But it significantly solves some of the problem. We can actually store a lot of data. Yeah.
Are you storing the key with the value then when you do the linked list, so that way when you come back?
Yeah.
Oh.
Exactly. So, but it reduces the overflow error. So if you want to store so many keys, we can do it with that, because it has every slot in the hash table will have a separate linked list. So the amount of actual storage will be much more. So the idea is to keep a list of all elements that hash to the same value. So here, like all the keys which maps to the same value have been kept in the same list. The array elements are pointers to the first node of the list. Each of the slot will actually point to the first node of that corresponding list. And whenever a new item is inserted into that, it will be inserted at the very front of the list. Advantages: better space utilization for large items, simple collision handling. Whenever we find a collision, and we just need to search the linked list, we gotta come up with the value. And as I mentioned, the overflow thing. So you can store more items than the hash table size. So this is an example which has like the key 0149 and so on and so on. So the basic hash function that we are using here, it's actually, we came up with this division method. So whenever we have so if we see that the keys that we'll be using are numeric, then the simple strategy that we use for coming up with the hash function is the division method, using the division method. So the only thing that we do, if we have a key k, so the corresponding hash function would be k model. So whatever be the key is, we'll do a modulus operator with the size of the table. So it will give us a simple hash value which we'll be using to store the corresponding key value pair. So here we have used a key percentile. There are 10 elements, so we've used this, and when we inserted 0, it got inserted in the 0th index because it's getting divided by modulus operator by 10. So it will be returning 0 to the 0th index. For 1, it go into slot 1 because 1 percentile 10 would be 1. And then again for 2, it got into 2, 3, 3. In 4, the first element, 4 percentile 10 would be 4. So that way it went to the 4th slot. But if we see that while entering maybe 64, we are also, the hash function is actually returning the value 4, which already has an element 4, right? So what it would do, like it would simply append to the front of the list. So this is a linked list, so we're just appending it. So every linked list contains a pointer, right? So that we are appending at the very front of the list. This item will have a pointer to the next one, like this. So that's how we are solving the problem of chaining. So there is one key thing that's called load factor. It is denoted by alpha. So yes.
Do you know the size of the table before we start hashing?
Yeah. So the size of the table that we'll be using, we'll be taking it we'll take that, the m. So there are some few points to mention how to take the size of the table. So sometimes during some method, while we'll be using division, it's told that we don't use the size of the table to the power of 2. It should not be taken like that. It should be something using less than that. So we'll be talking about this in the next class. It's like how to choose your table number, how to choose a good hash function and everything in detail. So here we have the load factor, which is actually represented by alpha. And it's actually the ratio of the number of elements in the hash table, the total number of elements which are actually stored in the hash table, divided by the size of our hash table. So it actually gives like the average number of elements like per linked list.
What if the hash function returns the same value for all the keys?
Yeah. So that's the worst case, right? So suppose I have written a terrible hash function. So whatever key I am putting in, it's returning the same result. So maybe I have just, for everything I'm returning 5. So every element, whatever I push, will go to the 5th slot. So that's a terrible case, and that's the worst case possible in chain. So for that, retrieval would require, like, I need to go and find, I need to traverse the entire list to find, in worst case, to find all the keys. So that's.
Is there a way that the hash function can be better in order to get?
So the basic thing is to come up with a perfect hashing function that would map everything into unique slots. For that, we need to know about the distribution of the keys in the universe, but most of the time it's not known and it's not possible to know how the keys are distributed. So that's a major flaw, or you can say that's a limitation to the technique of hashing, that we are not sure about how to come up with a perfect hash function. We can't. But there can be significant improvements on the part of the hashing function. We can use some primary numbers. We'll be using multiplication method to come out, actually devise a multiplication type of hash function, which will reduce, which will actually bring in more randomness to the hash function, and will give us more random values, and the chances of hashing will be significantly lesser. So this, everything that I've been talking about, it has been implemented using simple uniform hashing in mind, that all the keys are equally likely to go to any of them, and there is a high chance that there will be no collision and everything. But yes, in real world problem, there can be a terrible hash function, which will actually, in assignment 3 there is one like this. So whatever value you give, it will actually return the same value. So you need to have your collision resolution techniques to solve that. So alpha can be, it's not bounded by anything, it can be greater than equal to or less than 1. So because a particular chaining hashing technique can have larger values than actually the size of the table, so it's going to be more than 1. It can be less and it can be equal to as well. So yeah, so as you said, the analysis is like when all the keys are hashed to the same slot. So the time to search a key would be the length of the entire linked list, the worst case possible, and also the time to compute the hash function. So we are taking that, we'll be computing the hash function in some constant amount of time. So that would actually give us a theta of n complexity for the entire operation, if it's in the worst case, if all the keys are hashed to the same slot. The average case, it depends on the distribution of the keys. We assume that uniform hashing is taking place and everything. And if we, it's like for it's 1 by m for the probability is it can go to any of those slots is 1 by m, right? Like if m is the size of the table, so for each of the keys, 100, for n of them, it would be m by m. And if we take the size of the table like proportional to the size of the all the keys that would be stored, if we take like something like this, so it would actually come order 1 in average case. So I think so. This is something that I have for today. Next up, we'll be talking about in the next class. We'll be talking about hash functions and open addressing. So open addressing, we are not going to use any external linked list or something like that. It will be will be like rehashing, and there are three techniques: linear probing, quadratic probing, and double hashing. So we'll be talking about that, and also how to come up with what would be the size of the hash table and what would be the ideal hash function and questions. So before leaving.